Hello and welcome to this exciting series on modeling electromagnetic wave propagation in complex media. Whether you are new to simulation or maybe starting out or looking to deepen your understanding of how electromagnetic waves interact with different material, this series will guide you step by step through the entire process. In this series, we'll be diving into the electromagnetic waves, how it behaves as they travel through different types of media. We'll use COMSOL multiphysics as the tool which we'll use to showcase the different examples. And let us first think that why studying this topic is important. Well, electromagnetic waves are basically all around us. They are in radio waves, optical fibers, medical imaging, and even how our mobile phones communicate, and also like heat transfer and so on. So understanding how these waves propagate and interact with different materials is crucial for application in physics, engineering, and technology. So if you ever wondered like how to simulate wave propagation through materials, for example air to glass or even in biological tissue, this series is perfect for you. So basically our whole series is divided into subparts, and in the first part, our goal is to lay the strong foundation. We'll cover the essential concept of electromagnetic wave and discuss how this wave interact with different materials. Our focus will be mostly on the topics that are actually directly relevant to the engineers, those who are working on numerical simulation. This series is designed to be beginner friendly, so don't worry if you are new to this domain or you are just starting out to learn this particular concept. Each video will build on the previous one so you can follow along step by step and gradually develop your skills. Alright, so electromagnetic waves are a form of energy that travels through space. And they are unique because they don't require a physical medium like water or air or anything like that to propagate. These waves are made up of oscillating electric and magnetic field that are perpendicular to each other and to the direction of wave propagation. This perpendicular arrangement allows them to transfer energy efficiently through space, whether in a vacuum or through different materials. To understand wave propagation, let's start with few essential properties of electromagnetic waves. Three of the basics are the frequency, wavelength, and the speed, or we can say the velocity. The frequency, denoted generally as f, is the number of oscillations of the wave that occur per second, measured in hertz. The wavelength is represented by lambda, is the distance over which the wave repeats itself, or in other words, the distance between two consecutive peaks. The relationship between the two properties is very straightforward. Frequency and wavelength are inversely proportional to each other. As frequency increases, the wavelength decreases, and so on. The speed of the wave, denoted by v, is another important parameter. So if we take in vacuum, the electromagnetic wave travels at a speed of light, which is approximately 3 × 10⁸ meters per second. This speed is related to both frequency and wavelength by this equation. In vacuum, this speed is constant, but when electromagnetic waves enter a different material, the speed changes depending on the material property, which we'll discuss in a moment. Now, let's talk about the wave equation. This equation describes how electromagnetic wave propagates, and it derived from Maxwell's equation, which are the foundation of electromagnetism. In simple form, the wave equation shows the relationship between the electric field and magnetic field in a propagating wave. Here, c is the speed of light in vacuum. This equation tells us that any change in electric field over time will propagate as a wave. The same relationship applies to the magnetic field component of the wave. Electromagnetic waves also have an important characteristic known as polarization. Polarization basically refers to the orientation of the electric field as the wave travels. For example, in a linearly polarized wave, the electric field oscillates in a single plane. In circular polarization, the electric field rotates in a helical pattern as the wave propagates. Polarization is important when we look at how waves interact with different surfaces or materials, as some materials may only allow certain polarization to pass through. or may absorb specific polarization more efficiently. So let's discuss about material properties and how it influences the wave propagation. Two fundamental properties are permittivity denoted by epsilon and permittivity denoted by nu. These two properties determine how much the material resists the electric and magnetic field of the wave. Permittivity measures how a material responds to an electric field, while permittivity measures its response to the magnetic field. The speed of electromagnetic wave in a material depends on both permittivity and permeability. So in vacuum, permittivity and permeability have specific values, but in other materials these values are different, which in turn affect wave speed. This relation also leads us to the concept of refractive index, which is a measure of how much the wave slows down in a given material compared to the speed in vacuum. The refractive index directly affects how waves bend or refract when they enter a new medium. So when you're solving problems, you'll see that the refractive index can also be complex, and the imaginary part tends to contribute to the absorption of the wave. So just to show you an example, so this is one of the article I was just going through. I found this quite interesting. So this research article discussed the development of terahertz metamaterial with an exceptionally high refractive index achieved through advanced structural design. By creating a flexible, freestanding metamaterial, the researcher introduced a structure with a peak refractive index of 38.6 and a consistent low frequency value above 20. This high refractive index was made possible by enhancing the effective permittivity and reducing the diamagnetic effect through carefully designed metallic structure within the metamaterial. This approach involved the use of capacitive coupling in eye-shaped metallic patch embedded systematically to maximize charge accumulation, thereby amplifying the dipole moment. This advancement enabled the potential application of such metamaterial in area like compact lenses and slow light devices and so on. So like if you look at the graph, you can see like they have achieved quite a high value. So these are like few of the cutting edge application. If you understand the concepts properly of the refractive index, how to manipulate light in a particular structure, there are numerous possibilities. First, you can predict using numerical modeling, and then you can verify using experiments as well. So I thought it's better like I can show you one of the examples so that you get some motivation behind the domain. So that's all for this video. In the next video, we'll discuss about the various boundary conditions that we usually apply in numerical modeling. After that, we'll jump into COMSOL and learn some basic electromagnetic wave propagation models and try to simulate it. So do subscribe to this channel, and of course the playlist that is there for this series will be the first link in the description. And if you want to support my work, you can join and support this channel. So thanks for watching and have a nice day ahead.